All right, well, hello everyone. My name is Dr. Hillesheim. I'm going to be walking through with you guys for the second semester of organic chemistry for the summer of 2020 at FGCU. We are in unusual circumstances, I should say, right? Hopefully we're at the tail end here of the coronavirus thing. And so, with that being said, we're still delivering the lectures through an online format. I think this is a little bit new, especially for me. We had last semester to, kind of finish off the end of the semester there with delivering online content, but I certainly don't claim to be an expert, and so I say all that to say this. I'm going to be trying some new stuff as we go through, hopefully. This is a new setup for me also. I figured it might be a little bit easier to record myself as I walk through everything rather than just doing a voiceover with a recorded screen. And so things might change as we go along, and hopefully for the better. If there's something I can do to maybe deliver this content in a better, easier way for you guys, or if you want clarity or you need something, let's say resolved, if there's something I can do to help you guys out, all that normal stuff. Really what I'm trying to say is I'm here to help you guys out, okay? And it's awkward because you guys don't see me around campus, right? I can't really interact with you guys on a one-to-one basis. And so, reaching out to somebody that you see recorded on a video, might be a little bit weird, but at the end of the day, I'm here to help you guys out. Right? So anything that I can do to help you guys out in that way, just reach out and let me know. As we go through, right, we might be tweaking a little bit stuff here and there just to kind of make everything a little bit smoother for everybody. I might record a couple different lectures in different ways, but we'll just kind of see how it goes on. But the best thing you got to remember is that I haven't been able to get a haircut in a couple of weeks now, so you guys get to see the progress of how my hair grows as we go and deliver the lectures. So that should be something to look forward to here as we go through. Anyway, what we wanted to start out with was ethers and epoxides and thioethers, and that is chapter 13 in the textbook. So looking at chapter 13, and really we're going to be focusing on ethers and epoxides. And then, as we kind of finish through and go through and work through some stuff, we'll be getting to thioethers, just a little bit in there anyway, right? Now, one of the challenges that we have is that I'm kind of stepping in the shoes that somebody already else has been walking in. And what I mean is you guys have had another faculty member who's been going through and teaching you guys OChem 1. And so I make a couple of assumptions based off of that. One of the assumptions is that, the style of teaching that this other faculty member had is similar to mine, along with the expectations and the delivering, all this kind of stuff that goes along with that. For what it's worth, and as you guys will hopefully see as we go through, if we were doing this in a live course, it'd be a little bit different, right? And what I mean is, when I'm working with you guys in a one-to-one setting, right, in the classroom and stuff, I'd be interacting with you guys a lot more, be asking a lot of questions, making sure that you guys kind of are understanding the material as we go through. Can't really do that in a video, right? I can ask you guys a question and say, okay, everyone pause the video and, think about this. And, a number of you guys will, and you'll ponder and stop and think about it and then resume, right? But I really do need you guys to think about this stuff as we go along. I don't have to convince you guys, we're going through already in the second semester here of OChem, I don't have to convince you guys that this is going to be a challenging subject, right? You guys have made it through OChem 1, where you guys learned a bunch of information, right, in a very short amount of time because it's the summer semester, right? You guys learned about, three-dimensional modeling of things with enantiomers and diastereomers and all that. And then we learned about mechanisms and carbocations and shifts and all these kind of core ideas that come into how we can understand OChem 1. And so I'm expecting you guys to bring that into OChem 2, right? We can't leave that stuff behind. By the nature of what organic chemistry is, it is cumulative, okay? And that's what you guys will see when we talk about ethers and epoxides. The chapter right before this deals with alcohols. And so a lot of the same chemistry that we see with alcohols is going to get brought into this idea here. And so when I talk to you guys about, okay, an alcohol is an amphoteric functional group. And you guys are like, oh, yes, amphoteric, of course it is, right? Remember, when we're talking about amphoteric, we're just talking about it can act like an acid or it can act like a base, right? We've got an acidic hydrogen on there, and we've also got a partially negatively charged oxygen, which can pick up an acidic hydrogen also. And some of those ideas are going to be present here in the epoxides and ethers also, okay? And so that's what I mean, right? Please don't forget your OChem 1 stuff, right? It's going to be extremely important, and knowing the mechanisms and understanding them is going to make this so much easier for you guys, as you'll see in just a little bit as we learn the mechanisms that come out of this chapter here, okay? Now, if you're following along in the book, right, and we are on, just kind of starting out on page, where are we here? So on page 557, right, in chapter 13, the beginning part of this chapter will walk you through nomenclature. Now, I don't need to sit here and reread this book for you guys. So let me talk to you guys a little bit about my expectations and what my focus is. So if I were to mentally pull you guys through through this video, and I'd say, why are you guys taking this course, right? A number of you guys would say, well, I'm a chemistry major, so I need this for my, I need this for my major. Say, okay, that's fair enough, right? Some of you guys might say, well, it's just a requirement that I need to get through for my whatever biological sciences degree, and say, okay, fair enough, right? Some of you guys would say that you need this for med school, right, as a prereq, and that's fair enough. And all that to say is this, right? Every one of you in here, right, in this course, need to understand this at understand this material at a somewhat different level, okay? What I mean is this. So let's say that you're off to med school, right, and you got to go take the MCATs. So you're taking OChem 2 now. That probably means, MCATs are for, maybe in about a year to, anywhere from a year to 2 years from now. What are you guys going to remember in, let's split the difference and say a year and a half? Are you guys going to remember what you memorized in terms of, I remember memorizing how to name ethers, right? They have to have this ending and they have this priority and we put them together in this, right? You're not really going to remember that stuff, right? Memorization is unless you're doing it every day, right? If you just memorize something for the exam and then, you don't practice it every day, you're going to forget it, right? It's going to be a waste of your time, right? Because you're just memorizing it, it's in your, short-term memory, and then, right, it's off, okay? And so what I mean to say with that is I want to focus with you guys on understanding something. You're going to remember something that you understand, 1 to 2 years from now when you go to take, either your GREs, if you want to go off to graduate school, or if you, go and take your MCATs, if you want to take your MCATs, whatever it might be. You guys are going to remember what you understood, okay? Because those are concepts that we just kind of hang on with us. There's a conceptual side to naming that I'm not really interested in, right? There's programs that can name stuff for us. We can draw on molecules and it'll give us the IUPAC names. They're systematic, which means that what's in the book is what's in the book. There's no mystery behind it. So all that to say is this. Am I going to emphasize naming with you guys? No, I will not. Does that mean naming is not important? No, that's not what I mean either. You guys can read through the naming stuff just as much as I can. There's not going to be any mystery in there, okay? So that's just going to save us some time that, you guys can focus on other things in terms of, maybe some practice problems or if you have questions or whatever it might be, right? So all that to say, all that long spiel to say is that look through the naming stuff in here, please, okay? But it's not like I'm going to give you, on the exam, I'm going to say, name this compound. Well, you guys are going to have your books in front of you anyway during the exam, and so if there is a question on naming, there it is, right? So there we go. So we're going through, right, we're kind of, the first part of this gives us just an overview of the naming and kind of some of the properties of ethers. And so that's maybe where we'll pick this up, right? So let's think a little bit about what an ether is, okay? So generically speaking, right, this is what an ether is, where we have a central oxygen and we've got two groups on either side of that, right? R and R prime. R and R prime can be the same thing, right? We can have two methyl groups on either side, or ethyl, right? Or we can have an asymmetric ether where R and R prime are not equal to each other, okay? The difference is if one of those R's is a hydrogen, right, then we have an alcohol, Okay, so the only limitation we sort of have in this case is that R has to be some kind of carbon group. Okay, and so let's think about the implications of this for just a second. Let us take a look at maybe dimethyl ether versus something like methanol, right? So dimethyl ether versus methanol, okay? So the first thing and the most important tool that you guys can ever use, right? There's the most important tool that you guys can ever use is to look, right? To look and go, what is the same? What is different, right? What properties might come out of this? What theories or concepts have we discussed that can help explain the reactivity that we're going to see, right, with these things? And so I've already mentioned some of these things to begin with, right? So if we have an alcohol, right, remember when you have an alcohol, there's there's many important things I should say, but there's two salient features that we should always think about, right? Because we have an alcohol, we have an acidic hydrogen. That's extremely important. How many acid-base reactions did you guys talk about in the first semester of OChem? There's going to be even more of those in the second semester, right? So looking for acidic hydrogen is always, always, always important, right? So we have a fairly acidic hydrogen here. We've got a basic, right, a fairly basic oxygen here with a partial negative charge, right? So let's just put pen to paper, so to speak, right? We've got partial positive, partial negative. We have a setup for hydrogen bonding. We talked about how hydrogen bonding can affect transition states. We talked about hydrogen bonding and how they speed up or slow down certain reactions, especially with SN2s and SN1s and that kind of stuff, right? And so this same idea, or I should continue even, right? We have a polar section, we have a non-polar section there with the methyl groups, right? And you guys might have even discussed kind of the limit for alcohols in terms of solubility in different solvents, right? When do they become soluble in water, and when do they become insoluble in water, right? And so we have these different regions, I should say, of charges and polarity within alcohols. And some of that's going to carry over, right, into an ether, right? Now, the most obvious thing is we still have our oxygen there. That oxygen is going to be partially negative. That's going to be important, right? We're going to talk about the reactions of ethers, and we're going to build off of this principle right there. Now, obviously, we don't have an acidic hydrogen, right? So that removes hydrogen bonding from the solvent itself, but that doesn't mean that ethers can't hydrogen bond to something else, right? So if you make some kind of mixed solvent system, or you put them in with alcohols, we can see hydrogen bonding in some cases with these ethers also, okay? So important to kind of recognize that. But this is kind of going to be the main concept here, okay? We're going to see this main concept where we know that oxygen has a negative charge, and we're going to build off of that principle to do some of the reactivity here, okay? So when we continue on then, right, let's see what happens, right? Let's see what happens then on how to make an ether, all right? So let's look at making an ether here, okay? So preparation of ethers. Now there are a couple different ways of making ethers. Some are better, some are worse, some are better and worse based off of the context, okay? And so we do have to keep that in mind, right? One of the recurring ideas that we're going to bring out in the second semester of OChem is functional group tolerance. Now, if you go back to OChem 1, right, we talked a lot about here's one functional group, let's transform it into another. In the second semester, we're going to start to introduce multiple functional groups on the same molecule and say, I want to only react this alcohol over here. I don't want to react that amine. And so we're going to have to be clever about how we do that, because we have cases where alcohols and amines and whatever functional group you might think, they will all start to react if we put them under, let's say, acidic conditions, right? An alcohol is going to react with a strong acid, so will an amine, so will a carbonyl group, right? So will a cyano group, so will a grin, right? All these things are going to react under similar conditions, and so we're going to have to be selective about this, okay? And so we're going to start to bring that idea a little bit more and more as we go through, right? But let's think about preparing ethers and talk about reactions and that kind of stuff. So let's say that I've got alcohol, okay? And I put this alcohol under acidic conditions, okay? So I just generically throw some kind of aqueous acid in there. Well, it doesn't have to be aqueous, not necessarily, but you know, we'll just roll with that for the moment, right? So we got our good old buddy H+. Now there's a couple things to think about, right? So whenever you see an acid, right? This is kind of one of Dr. H's tricks of the trade, let's say, okay? Whenever you see an acid, typically those are going to be used in the first step, okay? Acids tend to be catalytic in a lot of cases. We tend to use them in the first step. They tend to form cations along the way. There's a lot of ideas that come out of just using acids. Now, pause, right? For those of you guys who are furiously scribbling down notes, or for those of you guys who have already tabbed over to another window at this point because I'm yammering on. Am I saying that every time you see an acid, you're going to use it in the first step and it's going to form a carbocation? No, right? I'm not saying that. Of course there's exceptions to this, right? But one of the things that we need to start looking for is trends, right? Patterns in reactivity. If this, then that, right? So what I'm saying is, for the majority of the time, especially as we go through the first 2 semesters of OChem, if we see a strong acid in the first, if we see a strong acid in our reaction setup, we're typically going to use that in the first step, okay? So let's see what happens. So we've got our good old buddy alcohol. We've got an acid around there, right? Let's make our alcohol act like a base. So it's going to reach out and grab, right? It's going to reach out and grab that acidic hydrogen there. So we do this. Fantastic, right? So we end up protonating our alcohol. So what do we notice here? Right? So what do we notice here? So now, right, if you guys are kind of following along at home here, right, we've done a couple of important things. So if I cover up that end of it there, right, we hopefully can see that this is water. Now, water is a fantastic leaving group, right? We're going to see it act like a leaving group quite often as we go through a lot of different mechanisms. And you guys have seen it act as a leaving group quite often. Okay? And that's in fact what it's going to do, right? But let's think about this for just a second. What flavor of leaving group is this? What kind of leaving group is this? Well, it's a primary leaving group. Now, if I have a primary leaving group and it leaves, right, what would I leave behind? So if I have a primary leaving group and it breaks its bond and it packs its bags and goes away, it's going to leave behind a carbocation. So if I'm a primary leaving group and I pack my bags and go, I'm leaving behind a primary carbocation. Is that something that's going to happen? There's 1 or 2 cases that we'll talk about, right? There's really only 1 or 2 cases where we'll ever leave behind a primary carbocation. The majority of the time, the answer is no. Well, nuts, right? Okay, so it's a leaving group, but it's not going to want to leave. So we have to give it the old boot out the door, right? So we're going to have to kick it out the door. So we're going to bring in something that's going to help make the leaving group leave. Now, here's the idea. So let's imagine this for a second, right? So what we did here is we have a beaker of ethanol, okay? And we took that beaker of ethanol and we added a couple of drops of some kind of acid to it, right? Probably sulfuric or something like that would be just fine, right? So we added some sulfuric to this. So what we have is a bunch of ethanol and we have enough acid to get everything going, okay? So this is essentially the solvent, and the solvent's kind of reacting with itself if you want to think about that, okay? So let's bring in another equivalent of ethanol here. We'll do that in green. All right, so we bring in something that'll help our leaving group leave, right? So we do this. So let's get all the colors right. So now we have this, and we kicked off our good old buddy water over here, okay? Right, so we brought in a nucleophile, not a great nucleophile, right? But it's around, it's in high concentration, there's a good chance that this is going to happen, right? So we can attack the carbon that's bound to the leaving group. What type of mechanism is this, right? What type of mechanism is this? That's important for you guys to recognize. So let me pause again for a second, right? If you guys haven't picked it up by now, I like to talk, right? So I like to talk you guys through what I'm thinking about when I look at this stuff, right? So we taught in Organic Chemistry 1, 4 or 5, maybe 6 mechanisms, kind of depending, okay? And the 4 important ones, right, are SN1, SN2, E1, and E2. Now, some of you guys just got cold shudders, right? You're like, oh my goodness, I hated that chapter, right? Or 2 chapters, right? That was confusing, and I have to remember all this stuff, and there were solvents and kinetics, and there were transition states, and we have to choose which one is it going to go. Yeah, right? But the thing is this. If you really understand those 4 mechanisms, SN1 and SN2 and E1 and E2, you're going to really start to see the components of those mechanisms show up again and again and again and again and again in the mechanisms that we start to walk through. Because those are very key components to other mechanisms. In fact, here's one right here, right? We generated a leaving group. It's primary, it's unhindered, it's going to be a very good leaving group, right? That's all ticking off boxes for SN2. Even though we've got a pretty cruddy nucleophile right there, okay? But we're ticking off all these boxes for SN2, so you know when SN2 is going to happen, okay? So please, 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 I think I posted, if not, by the power of working in advance, I will put up a review for you guys about OChem 1 and especially for the SN1 and SN2, E1, and E2 mechanisms, okay? But here we have an SN2 type mechanism. We generate the ether-ish, sort of, right, a protonated ether. We generate water along with it, but we've got to clean things up, right? You're never really going to finish things where you have a positive charge on an oxygen, right? That's not really something that's going to happen. So something has to come in and grab that hydrogen. So there's 2 options, right? The water can do this, potential, right? Or more likely, more of the ethanol is going to come in and grab that, right? Usually it's the solvent, so whatever's there in the highest amount, right? Let's do, purple seems good, right? Just for, to make things vivid here, right? So another solvent molecule comes in, and let's finish things up. At the end of the day, we generate an ether. We generate a protonated alcohol. I know what you guys are thinking. Hang on. And then we've got, I'm going to skip the colors, but I think you guys get the point here, okay? So there are our products, okay? Zoom in and kind of move over here for a second. Get that out of the way, right? So if we start with an alcohol, add some acid into it, we can generate an ether. What do we have here, right? Well, this is this guy over here. So what's going to happen? Well, this is going to continue on. Could the water come in and grab that hydrogen instead? Absolutely. Then what would we have made? Well, we would have made H3O+, which is what? A really strong acid. And what's a really strong acid going to do? Well, it's going to react with some alcohol, and it's going to continue on in this fashion, right? So we end up generating, either one of these 2 species ends up being protonated. We could make some argument about pKa's and equilibrium, and all that stuff would be extremely valid. But at the end of the day, I just asked you guys about the mechanism, right? We're not sitting here and analyzing in depth what happens here so much, okay? So there is the mechanism for an acid catalyzed ether formation, right? Starting from an alcohol, okay? Fantastic. All right. There's some problems with this though, right? There's some problems with this though. Really, this is only going to work best if we have a single alcohol component in the in our mixture, right? So if we try to make asymmetric ethers with this, we're going to run into a problem. So here's what I mean. So let's say that we wanted to go crazy, right? And we wanted to make this ether right there, right? So ethyl propyl ether. And say, I got this. This is easy, right? All I have to do is mix that, right, plus this, and throw in some H+, and I'll make my product, right? You guys see the problem already coming up here? What's the first step in the mechanism? Well, the first step is this is going to react with an alcohol. Well, which alcohol? Well, the one in black or the one in red. Is there going to be a difference? No, right? Now, some of you guys, well, the pKb of one of these alcohols, it's slightly more basic. Yeah, you're right, right? We could sit here and we could talk about the influence of the alkyl group and, you know, whether it's branched, all this stuff. There are subtle differences that we can make slight preferences for one of the alcohols over the other, okay? But the key word in there is what? Slight, subtle, okay? So if we do this, we're going to end up with what we scientifically call a mess, okay? So here would be a good pausing point and say, what in the world does he mean by a mess? Well, when I'm talking about a mess, I say there's going to be a lot of products formed. Can you guys go through and predict what the products are? Let's see, off the top of my head, I see 1, 2, 3. There should be 3 different products, I think, that come out of this, if I'm doing this right in my head, okay? So see if you guys can come up with those. Even better, okay, see if you guys can practice the mechanisms that come up with those 3 different products, okay? So let's do it real quick, right? What are the 3 different products? Well, the 3 different products would be this, right? The ethanol can react with an ethanol. And we make that product that we just did up there, right? In the previous couple of minutes. The propanol can react with a propanol. And then we get this guy right here, okay? And then we can also, right, one of our products is going to be, oops, I should, I guess, do that in black technically there, right? We can also get, I guess either way would be fine, right? It doesn't really matter, it could be red or black. We could get this product here, right? So those are the 3 products that I see coming out of this. Do you guys see the problem? The problem is I wanted just this, right? I want just that ether. So going through some kind of acid catalyzed ether formation, not really a clever way of doing this. Only if you want to make symmetric ethers would that be okay. And that's fine, right? Industrially, this is kind of how they go through and they make ethers. You know, there's obviously industry has more clever ways of doing it, right? But this is, you know, not a poor way of doing ethers, just not a selective way of doing ethers. So how are we going to fix this problem? Well, if we want to make asymmetric ethers, what we want to go through is something known as the Williamson ether synthesis. Okay. Now, the Williamson ether synthesis is going to build off of a concept from OChem 1. Okay. So here's how Williamson ether synthesis works. So if we take Mr. Generic alcohol, okay, it doesn't matter, right? I just use ethanol because, I don't know, it's the quickest to draw, so to speak, right? And we got to do 2 things, right? So I'm going to break down these 2 things into separate steps and then we'll bring them back together, okay? Step number 1. I'm going to throw in some nah, right? Now, what in the world is this, okay? So sodium hydride, right? This is our buddy sodium hydride. Now, do you guys remember what I told you is the most important thing for you guys to do? The most useful tool is to what? Stop, think, right, and look. This might be something completely new to you guys in terms of what this is here, okay? Or is, right now it's not that new, right? Because you guys have seen something very similar to this before, right? And so we just have to kind of use these concepts that we've thought of before and use them. We just have to apply them to something here, right? So let's think here real quick. We got our buddy sodium hydride. Now, what do we know about sodium hydride? Well, we know that whenever we've got a sodium, right, it's got a +1 charge, right? That's the way the world works. Unless you find sodium in its elemental form, it's going to have a +1 charge. And so if the sodium has a +1 charge, that means what? Whatever it's bound to has a -1 charge. So what we have is a hydrogen with a lone pair and a negative charge, okay? That's our good old buddy hydride, okay? So a hydride is H-. We have sodium hydride, NaH minus. We're going to come up with a couple different hydrides later on in the semester also that you do some different work for us. But you guys have already run into a couple of hydrides also, okay? So when you guys go through the hydroboration oxidation, right, we use a hydride in there also, okay? But don't worry, we'll point it back out as we go through it, okay? All right, so we got our sodium hydride, Na plus, spectator ion. Is it important? Yes. Is it participating in the mechanism? No. It's there as charge balance, so we're not really going to worry about it too much. It is around, it doesn't magically disappear, right? That's the only point I want to make. H minus. So we stop and we think, what do we notice? We've got the smallest atom that we can, right, a hydrogen, right? It's got a lone pair and a negative charge. So extremely small atom that has a localized negative charge. It can't resonance delocalize this. It can't spread the electrons out with inductive effects, okay? It's not a big atom, so we can't, make this we can't polarize that negative charge all that well, right? So we have a localized negative charge, which means two things: extremely powerful base, okay? When you have a localized negative charge, we've got a very powerful base, okay? And in some cases, in most cases, we've got a good nucleophile also. So whenever you have a localized negative charge, it tends to mean strong base and good nucleophile. The question is, what's the difference between those two, right? That's a very important question. And how do we know when something's going to act like a base and something's going to act like a nucleophile, okay? So very important. So let's think here, right? Powerful base, powerful nucleophile, what do we have? Well, we've got our good old buddy alcohol. Now, what do we know about alcohol? It has acidic hydrogen on there. So when we drop some sodium hydride into ethanol, the first thing that's going to happen is an acid-base reaction. Okay? So there's that. So what we end up doing, right, is making this. All right, I'm just going to draw it all out for emphasis. Okay. So negative charge on a hydrogen, in essence, get transferred to an oxygen. Is that a good thing? Yeah, right? Oxygen is much better at handling a negative charge than a hydrogen is. So there's a good, strong motivation for this to happen. The other thing is that makes this a really good reaction to happen is that we make this right here. My pen is starting to break, sorry. Right, that we form hydrogen right here, H2. H2 is a gas. It bubbles out of solution, so there's a strong entropic effect for this entropic drive for this to happen also, right? We increase entropy quite a bit. This is a solid, this is a liquid, we end up creating a solution, and we end up creating a gas, right? So this will bubble out of solution very nicely. So this is a very clean, efficient reaction, right? In fact, it's very exothermic at times too, and so we can, right? So be careful if you're doing this in the lab, right? Anyway, so what we end up making now is an oxygen with a lone pair and a negative charge, right? With an additional lone pair and a negative charge. What do we know about those? Right? Well, the same kind of analysis, right? We don't have any resonance, so we can't spread that negative charge out. There's no inductive effects that are working here, right? There's not electronegative atoms drawing things away. There's no resonance. It's a somewhat smaller atom, right? Oxygen's not all that big, right? So we've got a localized negative charge, right? So again, we have a strong base and a strong nucleophile, right? And I'm kind of giving you guys these clue words here because these are things we should be paying attention to when we start to predict what happens next, right? So here's step 2. So here's what we're left with, right? Now in step 2, I bring in, let's do this, right? There we go. Now I bring in a alkyl halide. Now this isn't any normal alkyl halide, right? This is a specific alkyl halide. We've got a good leaving group. It's primary, okay? It's not very sterically hindered, right? There's not a lot of junk that's next door here blocking things, right? And so this is where you guys should pause and say, aha, I've got a strong base, a strong nucleophile. I've got a good leaving group at a primary position that's unhindered. And you need to go, SN2 reaction, okay? And that's what's gonna happen, right? We're gonna do an SN2 reaction here. This is gonna come in, pop that out, and now we are left with, whoops, that should be in black, and here we go, right? Plus Br minus, plus Na, right? Plus here, okay? So we've got those two around. Perfect. So this is the magic that happens, right? This is a Williamson ether synthesis. We deprotonate, step one. Step two, we add in the appropriate alkyl halide, okay? So let's bring these two ideas together here and kind of talk about how, or at least give an example about how it's shown in the book. We have this, typically, right, 1 NaH. I'll do this in red since that's what I did. 2, we add in the alkyl halide, and then cool, and there's our product there, okay? Now, what do the 1 and 2 mean, right? Remember the 1 and 2 here mean we have two separate reactions, we just kind of put them together. Why do I have to put these as separate steps? That's a very, very good question, okay? Can you guys figure it out, okay? So see if you can think about why I have to put these as separate steps and I can't put them together, okay? If you can't figure it out, drop me an email or something like that, okay? I don't want to, I could spend hours with you guys here and that'd be fun, except I also have to move this along with you guys also, right? But think about why I have to put those as separate steps. The first step, I create my negative charge. The second step, I do my SN2 and I make the ether. Now, we made a symmetric ether, but we can make whatever and bring in whatever alkyl halide we want there as long as we can do an SN2 reaction with it, okay? As long as we can do an SN2 reaction with it. Got it? That's the limitation. We have to be able to do an SN2 reaction, okay? So you can't bring in some tertiary alkyl halide, right? So I can't do something like this, where, just for argument's sake, right, just for simplicity, I can't do this, okay? What's the product gonna be here? I'm not saying a reaction doesn't happen. What's the product gonna be though? Okay. So, product for this, right? Probably this is going to be the dominant product here, okay? How did we get there? What mechanism did I use? How do we know? How do I know that's the product? How do you guys know that that's the product, right? That's the real question there, okay? So there's Williamson ether synthesis. That's kind of one of the big mechanisms and ideas that come out of this chapter, okay? So one last thing before we kind of wrap up this first video here. Let's come up with one more clever way of making an ether, right, before we kind of go into the even more clever ways, right? So let us start with a generic alkene, okay? And let's do a quick review question then. I want you to turn this alkene into an alcohol. Okay, I want you guys to turn an alkene into an alcohol. How many different ways do you guys know how to do that? Right? Well, there's a couple ways, right? We could do a hydration, acid catalyzed hydration. We could add some of the appropriate acid in there and it could go through its mechanism and do its thing. Hopefully you guys remember that. That's OChem 1 stuff. Again, if you guys aren't following along, just drop me an email or whatever it is, right? That's fine. So we could do acid catalyzed hydration, okay? And one of the other methods that we learned, right, one of the better methods for, maybe a lack of an adjective, right, is the oxymercuration, demercuration, right? Which looked something like this. Where we have some kind of mercury salt, right, Hg. Mercury acetate is kind of what they use in the book, right, OAC there, right? You have some water along with that, and then you come back with sodium borohydride. Aha, right? So we did learn about another hydride in OChem 1, okay? So this is another hydride source there. You guys likely didn't learn this mechanism, right? I'm not saying that it isn't important, it's because this second step there is right, a little bit wonky about how that works. First step you guys should understand and go through, and we'll talk about that, right? But this is a good way of making an alcohol. What is so important about this reaction though? Well, the key thing, right, is that we generate an alcohol on the more substituted carbon, okay? So a Markovnikov addition, right? We remember all about that stuff, hopefully, right? So we generate an alcohol in the more substituted position, no carbocation intermediate. That is key, okay? It's key. Because remember, if we have carbocations, we have rearrangements and shifts and movements and all that kind of stuff, okay? So I'm gonna change this up drastically. You guys ready? So instead of water here, right, watch, instead of water here, what I'm gonna do instead is add an alcohol. And then I drastically change my product. So I have some kind of mercury salt with an alcohol instead of water, and then I come back in with sodium borohydride. Wow. That's just nuts. Does the mechanism change? No. Right? The mechanism is going to work in the same way, right? We make some kind of mercury intermediate, right? It's a 3-membered ring mercury intermediate. The alcohol comes in from the opposite side at the more substituted position, right? And then we clean it up with the sodium borohydride. We get rid of the mercury, and we're left with the ether at the more substituted side, okay? Do you guys see the difference here? Now what happened? Well, we've got a little bit more of a, some more bulkier groups around here, right? We can kind of effectively increase our capabilities, how we can make ethers, okay? So 3 ways that we learn how to make ethers, okay? 1 is symmetric ether, just having alcohol with some acid. 2, the Williamson ether method, which is the preferred way of doing it, sodium hydride followed by an alkyl halide. And then 3, using oxymercuration, demercuration with an alcohol rather than a water molecule there, okay? So I think that's a good pausing point. After we'll, in the next series of lectures, we're gonna go through and we're gonna talk about some of the reactivities of ethers, okay? And so that's it. I will see you guys next time. Thank you.